got this special opening, very special opening for you today. This one's because we're going to see sparks, we're going to see arcs, we're going to see smoke. We're going to see this unit go boom. Oh, it's going to be a special one. I tell you, you're going to like this one. And we're going to do forensics to see exactly why it went boom. So let's get the show started. This time I have a Panasonic microwave oven. This one's an inverter type, and I was told that it picked up the nasty habit of smoking. So we're going to plug it in and see what happens. I'm going to plug it into the dim bulb tester on dim mode just in case there's a short. No light. There's nothing, it's dead. But I understand the light still worked when it was opened. And the light does work when it's opened. You can see the light. So it's not a blown fuse. The display is dead. Oh, it beeps. What the heck? It beeped, but the display is dead. I wonder if it's just the display that's gone out. Does this thing try to start? Let's see here. Just try. It won't do anything because it's on the dim bulb. All it'll do is turn the light on. Oh, it's trying to do something. Well, what the hell? It was dead last night. The display is out. I wonder if it's just something with the display, because the display is out. But that thing tried to come on. We saw the dim bulb when it tried to start it. It beeped, and when I tried to start it, try it again, you'll see the dim bulb. See? It's trying to start. So it's not a dead short. So what the hell's wrong with it? But the display is completely dead. Remove the back. Yes, that's a security bit. Should just pop apart. So this is an inverter microwave. I don't think there's anything wrong with the inverter, but we're going to power it up under full power. The display is out. It might just be the backlight that's out on the display. I think it's an LCD on this one with probably a backlight, so it might be just the backlight is out. But I'm going to power this up on full power, away from the isolation transformer. I'll throw a glass of water in here, just see what it does. Again, I picked it up last night. This is a relative's. And she said there was a bang and there was a bunch of smoke, but maybe she just boiled something up inside it and got a bunch of steam, and maybe she confused steam with smoke, and maybe that took out the display, because the display is certainly completely dark on it now. But when I was at her place, I pushed buttons and it did not beep. So maybe the keypad had too much moisture in it and it just wouldn't run. Because when I picked it up last night, I noticed that the light came on, and but it didn't beep or do anything. I tried unplugging it for like 2 minutes and plugging it back in. The light still came on and didn't do anything, so I brought it home, and then I got a phone call saying that I knocked out the power to her fridge, which I can't see that happening, because I don't think that in condos they put the microwave on the same circuit as the fridge. That would kind of be against code. They need to have their own circuit, but that's what was claimed, as I blew the circuit for her refrigerator. Got a cup of water inside. I'll plug this into my 15 amp circuit with a 20 amp plug on the end. And I'll just set this thing for, wonder, can I shine a flashlight on here? Can I see light from behind? Let me grab a flashlight. See if I can shine a light from behind this thing. I don't see anything lighting up on here, but is it a backlit? This might be oh, it's a backlit display. I don't see anything on it though. What happens if I push? Power level. Power level? Okay, I can see P10. So yeah, it's a backlit display. Look. If I shine the light on here, can you see P10 showing up? We'll get another shot. You see? It's lighting up. It's just, it's the display is out. The bulb is out. Okay, how do I do this thing? I'll just put it on for like 1 minute. That's 10 minutes. Let's stop that. Can I just do 10 or 1 minute? That should be power level 12. Start. Oh. 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 Houston, I think we have a problem. Oh, magic smoke. Let's try that again. Are we going to see any magic smoke come out of this thing? I can smell it. I can smell it from here. Something's burning up in here. You hear that? An electrical smell, and then it shuts off. We may have a bad magnetron on this one. Either a bad magnetron or the inverter's gone south. Can we see where things are burning? That's what I'm wondering. I can smell it. Ah, wonderful. It's coming from the inverter. It's coming from the inverter. The inverter is toasty on this. Probably capacitors. It's probably ceramic capacitors are cooked in here. You know what? I know someone's going to criticize me for turning this thing on again, but oh, smoke! Smoke, smoke, smoke. It's smoking down here. Let's pull the shield out. I'll unplug it first. You see, the owner of the unit has another microwave already. So, unless I can get this thing going without having to put a bunch of parts into it, they're not going to fix it. If it's just capacitors that are bad, and I can get some, then we may be in luck. But if it's a transformer or something that's smoking, then I don't think we're going to be fixing this. When I was in the business, when these things popped, they didn't have any service kits available. Back then, the inverters were still brand new. If we had an inverter failure, it went to, the entire inverter was replaced. Wait, I don't have to take the inverter out. I can pop this cover open. That's what I need to get to. I need to see underneath here. There we go. Let's see. Let's put that ground screw back in. I want to see where the smoke was coming. I think it was right in here. Very important screw, this ground screw. Right down there. Yeah, let's see. It might be one of these caps has gone bad, right? Or something in here. Well, let's just see where it goes bad, where things go south. You can also unplug the magnetron too. Could be a magnetron that's shorted. That could do things. Okay. 5 seconds on the clock, please. Let's observe what happens right down here when I hit start. Oh, you know what? It's the transformer that's shot. That's where the problem is. It's the transformer. Take a look down through here. This has got like a little flyback transformer in it. We're going to look right down inside here. Where are we going here? 5 seconds on the clock. I'll just lower down the camera. Okay, now with the magic of a handheld camera off the sticks, take a look down in the middle of that transformer core. Ooh. Ooh. Oh yeah, it's looking great. It only runs 5 seconds and then shuts off. PU. It stinks in here now. Good thing the door's open. Yeah, I think it's toast. What do you guys think? You think this one's toast? I know this one's toast. Why it failed? Who knows? It could have been the magnetron went bad and shorted it out. We could unplug the magnetron. Down here, there is a plug. There should not be any juice on here. Famous last words, that's how I got electrocuted, was from a microwave oven. Threw me across the bloody shop, like about 6 feet. Yeah, it was the only time I ever got a jolt was from one of these bloody things. Let me unplug that magnetron and we'll just fire it up without the magnetron plugged in. It's still going to go bad. It's the transformer that's shorted. But what I don't know is, was it caused by the magnetron? The magnetron itself could be shorted as well. We can measure that though with the meter and see if there's a short in it. The magnetron, as you can see, is unplugged. The inverter's shot anyway because it's arcing. But you can see. Whoa! You guys want to see smoke? Holy shit! It went up good. Like, holy crap. Can we do some more? I only put it on for 5 seconds. It didn't even shut down. So obviously it was producing power. And what was happening was the magnetron was trying to come into load. I bet you the magnetron shorted. And the magnetron failed. And it took out the inverter. As they say, the owner of it said that's what happened in her kitchen. She said it smoked. So it's not that I blew anything up. It was like that when it came in here. But let's just make some more smoke, shall we? Woohoo! Okay, I think that's enough of that. It's probably caused myself cancer down the road. We'll measure this thing, see if there's a short on the magnetron. I bet you are going to find that the magnetron shorted, and that's what the failure was on this. So I'll be able to salvage a fuse out of this thing, and then the rest of it's going to go to the bin, because they are certainly not worth fixing. I'll keep the light bulb, and I won't even bother with the timer board because the light's out on that anyway. The backlight's out, it doesn't light up. Or if it does, it's really, really dim, but I couldn't see it. In here, I bet if I turn out the lights, it might be very, very dimly lit. Let's see. Yes, it is very, very dim. It's not that the backlight is out completely. It's really dim. That's why I couldn't see it. I couldn't see it at her house because it was bright in there. And then with the shop lights on. So the LED backlights are just about completely shot. Shall we have some fun in the dark before I condemn this thing? Turn out the lights and watch this thing cook. Where's the start? That's enough of that shit. Okay, back to the overhead camera. Let's check the magnetron for short circuit. Put the infrared camera on this thing. I bet it would light up like a Christmas tree. Should we have some more fun with this thing and make some more smoke? Okay, I got my, I'll just put this on ohms range. There will not be any charge, obviously, on this thing because it's disconnected, but we're just going to measure between the anode and the cathode, or filament, or whatever. Let's see if it's shorted. Maybe it's not. Maybe the magnetron's okay. It might be. Magnetron might be okay. There's only one way to find out, and that would be to put this in another oven. So what I'm going to do is I'm going to, because it's not shorted, right? We'll get a short between these two pins, obviously, because that's the filament, right? So we'll see the filament. It'll show up as like a dead short, which it does. But there's no short between the anode and cathode. It doesn't mean that it's not shot, but it means it's probably not shot. I think what happened on this is just the inverter itself went bad, and that's where our fault is on this one. Want to see some heat? Let's turn on the thermal camera. I'm not ready to kill it. I'm not done killing this thing yet. Well, we can already see it's hot. Let's just get it a little more heat. I guess nothing else shows up. It's already hot. You can already see the heat on this thing. Oh, I can feel the heat on this thing. It's cooked. This thing is toasty. I can feel the heat from like 2 inches away. It's so hot. Okay, I think we're pretty much done on this. I'm going to salvage what I can. I'm going to salvage the magnetron. I'll salvage the light bulb, even though I don't really have a use for a light bulb like this. My microwave uses an LED. But inverter shot. Fan might be worth salvaging. It's always nice to have a little electric motor, a little fan. So I'm going to obviously salvage the fuse because These microwave fuses are not cheap. My neighbor had to get one of these. He came over the other day asking if I had one. It's an ABE, what is it, how many amps? 250 volt. This one's only 15 amp, but it's an ABE type fuse. It's a slow blow, sand-filled fuse. My neighbor came over asking me if I had one. I said, no, I don't. And the microwave he was dealing with, it used a 20 amp, but still, I sent him to the local appliance place to get a fuse. And they charged him $18 for a fuse. So I'm hanging on to this one because it's not blown. And it's worth 18 bucks. I'm going to salvage the magnetron and maybe keep the light bulb from here, because this unit is going to be going in the junk. Oh, this is the light bulb that's... What? It doesn't unscrew. Are you kidding me? Like, are you absolutely shitting me that this light bulb doesn't... This is it? Like, the bulb doesn't unscrew. The bulb is soldered in place. What the hell? I shit you not. That bulb does not unscrew. That is a replacement. You would buy the bulb with the base, and it has just the two spade connectors. Unbelievable. Incandescent bulb that will burn out after a while, and we used to be able to buy replacement bulbs. Now you got to buy it as a complete assembly. I'll hang on to that. I don't know if I ever need one, but I definitely will hang on to it, because that being a specialty part, it's going to be one that's hard to find. We'll pull the magnetron out, because if it's good, which there's a good chance that it is, this is something worth keeping. For sure. I'm going to get there's a couple screws down the back here. I think I can get them from here. Now, magnetrons themselves have hazardous material in them. I will talk about that in a minute. It's a compound called beryllium oxide. I think that's what it's called. It's the insulation. It's like a ceramic material that surrounds the antenna, and you have to be quite careful that you don't break it or scratch it, because it releases a dust that can get into your lungs and cause cancer. Wish I knew that before my former co-worker, the brilliant man that he was, broke one once. Actually, it was one of my former co-workers. We had a young guy working for us, who wasn't the sharpest knife in the drawer, say. Guess that bracket wants to come out. Wasn't the sharpest knife in the drawer. Am I allowed to say that these days? Was a few cards short of a full deck, a few fries short of a Happy Meal. I'm gonna get all the wokers up there now. I'm safe as long as I don't say the R word, right? Anyway, this fella was a dim bulb, and young guy, a kid, right? Like in high school. This thing's still hot as hell. Anyway, he wondered what was inside a magnetron, and proceeded to break the thing open. At least he didn't use a grinder or a hacksaw. He just used a hammer to hit it. But he proceeded to break the antenna off of the magnetron. Now, you don't want to do that, because even doing that, you can release dust. But at least he didn't put a grinder on there or hacksaw or something, because that would have released a lot more. But anyway, this winner decided to cut in because he wanted to see what was inside, which was disappointment. There was nothing. There was a vacuum inside it. It's a cavity and a vacuum. And it went pop. Actually, I think the vacuum was already probably just take that whole thing off rather than fight with these stupid connectors. Probably should keep this too. It's the thermal cutout, so that you have something catch fire inside. Like if you overcook your popcorn and you catch the popcorn on fire, this will overheat. It's a 105? It looks like 105 Celsius. So if the interior gets over 105 Celsius, it kicks open. And it's probably a self-resetting one, this one. Some of them were self-resetting and others were not. I think this was probably a self-resetting one, so that if something got too hot inside, it would just shut down. Jesus, that smoke is giving me a headache. Whew, it still stinks in here. I got the door open, right, so I got ventilation. But certainly, that ought to stink, that's for sure. Okay, this whole fan block should just lift out of here. See, I don't have to worry about putting this thing back together because this is going to go right to recycling. There. That's the fan. As you can see, the wires inside a microwave are not all that heavy. Look at how thin these wires are. People say, "Oh, look, you need it. It'll handle 15 amps." Well, these little wires here handle 15 amps, no problem. Always good to have a fan. So I will hang on to the fan. All right, 2 screws to open this up. Or remove it. There's another one down here. This is a 2M261M32 microwave or magnetron, which is quite a common one. There's just a couple different configurations, and mostly what they are is if they're top mounted or side mounted, and the orientation of the mounting tabs. That's the big factor, and the polarity. So this one here, there's the magnets. That's why the kid at the shop wanted to break the thing apart. He wanted the magnets out of it. He wanted these magnets. So you get your filament on this side, and then this is your filament plus your anode, and then the cathode's actually the body of the unit itself. That's how it works. Anyway, there's a chamber inside here with magnets on either side with opposing, I think it's opposing magnetic fields. So like north and north fields are opposing. I think that's how they were. I'd have to break one apart to see whether they push each other apart or try to attract each other, but I believe they were opposing forces. Somebody might correct me. That creates oscillation inside the waveguide. It's got a tune cavity in it, and microwaves are the result. Microwave energy is the result, which radiates out this antenna. This is the antenna that picks up the radiation, the microwave energy. That's the RF gasket to stop leakage between here and the actual antenna. And this is just into a cavity that goes into the oven. There's nothing else in there. If you were to open up the grease plate that covers the cover, you would see this inside. This just goes into an open waveguide, which is just a cavity that goes into the oven. That's all they are. This is what generates the RF that cooks your food. Well, correction, doesn't cook your food. Causes the water and fat molecules in the food to oscillate at 2.45 gigahertz. I believe that's the frequency that they're on, 2.45 gigahertz, just above your router, your 2.4 gig. Actually, to be precise, your wireless routers have 11 channels on the 2.4 band. Actually, they used to have 13 channels. But you see, Wi-Fi channel 13 is dead center to the frequency that is transmitted from your microwave oven. So if you tried to use channel 13, you would get nothing. Every time someone turned on a microwave oven in the neighborhood, you would lose your signal. Well, maybe not in the neighborhood, but you get the drift. The ovens are not completely RF tight. There always will be a little bit of leakage, but that leakage is not harmful because it's very low power, and your wireless router puts out more power than what microwave ovens are permitted to leak. But if you were using channel 13 and you were turned on your microwave oven and you were somewhere between, or the oven was closer to your device, like your phone or your tablet or something, the amount of energy that was radiated from just getting through the door would easily kill the signal from your router. And that is why routers no longer use channel 13, even though a lot of the programs will actually show up to channel 13, like a lot of the Wi-Fi analyzer programs will actually show up to channel 13. You can't even set it on your router. Now, I guess if you flash the firmware, you probably could, because 13 channels are still listed as usable channels. It's just that the router manufacturers stopped putting channel 12 and 13 on just because of the mutual interference. And even though channel 11's sidebands will actually ingress into the channel 13 space. So that's why channel 11 is always, or one that's not as good as far as interference-wise as, say, channel 1 or channel 6. Those are the best ones. 1, 6, and 11 is what you use on your router, but typically 11 can get some interference from other devices, such as microwave ovens. Not to say that 5 gigahertz is any better on your wireless router. Something to take note while I'm talking about radio interference. On your wireless router, your 5 gigahertz band is split up into 3 groups of channels. Channels, I'm going to say, I think it's 32 to 64. I could be wrong. I have to look and see. Let me look and see. Let's get my numbers right here. 2.4 gigahertz. So you can see it shows right up to channel 14, actually. But nobody's really using anything above channel 11 because the routers, unless you modify them, won't go that high. But your microwave oven is like right up here. Be nice. If the microwave was on and operating, I probably would see a signal in here somewhere. Or no, I wouldn't see it on this, because this only responds to actual Wi-Fi channels. But what I would see was, if I was using a spectrum analyzer like Wireshark, for example, I would see when a microwave came on, I would see a signal. Not a broad signal like this, but just like a single signal on a spectrum analyzer. Okay, so there's our 2.4. The 5 gigahertz channels 36 to 64 is one band. One of my neighbors is on there. And then there's another band. There's a whole big empty space between 64 and 100, which is not part of the Wi-Fi band, and that's why it's blank. And then they start again at channel 100 and they go up to channel 144. Look, there's nobody there. Gee, I wonder why. I'll tell you why in a minute. And then you've got this nice crowded band, 149 to 161. And somebody around here is a dick, apparently. So on the Wi-Fi 5 gigahertz band, channels 100 to 144 are pretty much unusable, at least if you live near the coast, or near an airport, or near a weather center where they monitor the weather. And the reason why is the frequencies between channel 100 and 144 are shared. It's what's called the DFS, which is a shared band. It's shared with marine and weather radar. You know, the Doppler radar that they show on the TV news, for those of you that watch TV, that shows where the rain and moisture and so forth is. That Doppler radar is putting out an incredibly powerful signal on the 5 gigahertz band, as do boats, even small pleasure craft that have radar, but for sure the bigger boats, ferries, tugboats, ocean liners, transport ships, container ships, etc. They all have radars on them, and the radars operate in the same frequency band as the 5 gigahertz Wi-Fi band between channels 100 and 144. And what happens is, if your router detects any radar interference, and it can detect it because radar is a very unique, distinct signature. It's a pulse. It's going on and off rapidly. If your router detects that you're operating on a frequency that radar is on, your router must cease transmission and move to another channel, which is another one that's generally going to be in that same band. So you're good for another little while until another boat goes by that radar happens to be operating on that frequency, because all the radars operate on a slightly different frequency so that they don't interfere with each other. So yeah, if you're using 100 to 144, you're going to experience dropping. you're going to experience your 5 gigahertz band dropping. And we can't use it around here because we're near the coast. And 9 times out of 10, when I get sent out on a trouble call with a customer at work complaining that their Wi-Fi is bad, I find that the router is on auto search and it's picked a channel in one of the DFS bands, and I go and manually change it to 149, and the problem is solved. Also, there's the power level. So on the 5 gigahertz band, there are 3 power levels that can be used. One of them is 250 milliwatts, which is on the channels 36 to 64 range. And then there's 200 milliwatts on the 100 to 144 range. And then there's a 1000 or 1 watt that's on the 149 to 161 channel range. So guess which channel is going to give you the best signal on the 5 gigahertz band? It sure as hell isn't the low band or the mid band, it's the high band. And one of the reasons that they allow more power on the high band is because the higher frequency signals don't penetrate walls quite as well. So the theory is, well, on the low band, being it's down around 5.2 as opposed to I think it's 5.8 or 5.7 gigahertz, 5.2 should penetrate walls better than 5.7. They don't. Not much. There's not much difference in the penetration between 5.2 and 5.8 gigahertz as far as penetrating solid materials. The power makes a difference. So a lot of routers will have a signal in the low band, like between 36 and 64, and another one in the high band, which is, if it's on auto search, it'll be between 100 and 144, unless you switch it manually, as a rule. I'm coughing because of the smoke that's still, like, it's been like half an hour. I can still smell that transformer, and it's still hot too. It's still warm. This thing, like, this got good and hot when I ran it there. We'll pull the inverter out now. I want to just tear this thing down because I know you guys want to see that. You want to see this thing come apart and see the toasty components in there. So, which we know is the transformer. So I'll remove the ground. I'll also save the switches on this too. That's another thing I will save is definitely the switches. Maybe even that door hook, because these parts are quite scarce. They're hard to get these days. Okay, this should just pop right out if I pry this thing off. I think there's only the one screw. Get that magnetron out of the way for now. Oh, and I don't know, did I mention it? But this is this pink, looks like ceramic. This is the beryllium oxide. So you don't want to scratch this or break it, because microscopic dust can come off, and if you inhale it, it will get caught in your lungs and create some problems down the road. Like what happens if you inhale asbestos. You could end up with cancer, lung cancer. Mesothelioma, or whatever those nasty ones are from industrial stuff. But with a bit of coaxing, this whole unit will pop out. Okay, what's hanging it up? The wires for the turntable, of course. Alright, okay. Unplug the power line for it, that's the timer control. And then this is the power going into it. Okay. Okay, folks, we know the transformer is where the smoke was coming from. Let's just pull that board. Is there anything burned on the bottom? Here's the board. As you can see, there's nothing toasty on the bottom here. There's a drive IC. They didn't even bother to put a heatsink on it. Not needed. That's just driving the PWM signal for the phase control for the MOSFET here that switches on and off. Oh yeah, it's got a crack in it. That's probably what happened. You see, is that a crack? It looks like a crack. Yeah, it's got a crack on the core. Check this out. This is probably what happened on this thing. See the core? The core is cracked. So something caused, I mean, this, for whatever reason, that core cracked. I mean, that's probably why it failed, was when the core cracked, it ended up with a hot spot. Part of this got very hot, and melted the insulation of the winding for the high voltage side. Might have even been on this side. It could have very well been on here. We'll pull the transformer out. I want to unwind this thing because, you know, this is kind of a teardown diagnostic forensic now. So I'm going to pull the transformer and we'll unwind it and see where the short is. While I'm waiting for the soldering iron to heat up, I'll salvage the switches and the bracket, because we know that they're still good, and that will just save me from having to buy one down the road. Just unplug the whole harness here as well while I'm at it. I won't bother with the timer just because the light's out on it. Oh, what the hell, maybe I'll take that too. It's already undone. It's got a relay on it I could use. The guy at the recycling place won't be happy when I show up with a shell of a microwave and say, here you go. He'd be like, where's the rest of it? I kept it for parts. Well, at least the fan still works. Lead free, so it says. Okay, I got to take out a couple big lugs over here. This might take a while to heat this up with my dainty little, I think it's a 60-watt iron, but it should do the job. I'll just crank it up. Might take a while. That's a good sized lug. Plus my tip is kind of oxidated a bit, isn't it? Clean that off. Put some fresh solder on there and transfer the heat down. Yes, you put new solder on to heat the old one up, to melt the old stuff. I will admit that this new solder pump works a lot better than the one I had for years. I had a solder pult at the shop, a little black one, and I knew they were good, although I didn't know how good the new ones were. This one is a knockoff. An original solder pult is like 50 bucks at the local shop, and this one was like 25 or 22. But it seems to do the job just as well. Lots of suction on here. Maybe I'll just cut these ones because they're bent, so I'd have to straighten them anyway. So I'll just use the good old side cutters and cut them off. As the transformer shut anyway, so it doesn't matter. Cut that one. And cut that one. I think those are the only two, and then this thing should just, this bad boy should just lift right out. Oh, there's a couple more down here I gotta cut. Oops, I broke the board. Uh-oh. Not that it's ever going to get used again. It's going in the scrap heap, this one. All right, let's take this transformer apart. We'll find out where the damage is. Just cut some windings. Stack diodes are probably okay. high voltage caps that are rated at 3 kilovolts are probably okay. So this uses capacitors and diodes in a doubling circuit. I love how they just melt. They just put these in place and melt the plastic on them. Okay, so those are a couple caps there. I'm just trying to get this plastic out of the way so that I can unwind the transformer, unwind the winding and see where the burnt winding is, because, well, we know it's burnt. We can see it arcing. But was it the primary side that went bad, or was it the secondary? But the only way to find out is to take out this broken core. That won't be too hard considering it's broken. Oops. Good thing I have glasses on. Could have lost an eye there. See, what I think happened on this is this core cracked and caused heat to build up. And once heat built up, it melted the plastic. That's what I expect to find. I expect to find it's probably melted in here and caused the insulation to melt, and then the transformer started to arc. That's what I think happened. I might be wrong, but that's what I think happened. And I think I'm right. Because you can see an awful lot of heat that happened in here. And if we look at the other side of this where it's burnt, you can see right here is where it all burnt. Oh, it is on the secondary side, the high voltage side. But right here, right where that core broke, you can see right down in here. So let's just let's push the rest of this core out. It should just come out. I may have to give it a helping hand. In other words, break some more plastic out of the way. It's glued in place. They glue them so that they don't resonate. Otherwise people would scream, because the transformer itself would be buzzing, so they glue them together. But you can see what happened on this. This core broke. This core cracked. And there's the hot spot right there. This piece shattered. This got red hot. You can actually see how hot it got. It fused, and inside the inside here, it burned a hole inside here, which then burned a hole in the winding. We'll take out these windings here. These will come out quite easily. We'll just pop these out, unwind the primary. Look at how beefy this core is. It's not very long, this wire either. This is basically switching 150 volts or so, whatever the rectified AC is, on and off. So that's the winding. How long is this thing? It's like 6 feet long. Just a little over 6 feet, this wire, but it's made up of multiple strands of fine magnet wire. So they can pass a lot of current through here. This is going to be handling, you know, probably 15 amps or damn close to it at high frequency, switching on and off at, you know, maybe 100 kilohertz. But that's the primary. That induces the magnetic field into the core, which is then transferred to the secondary winding over here. And now we will undo the secondary windings and see where it's burnt. Secondary winding can be much longer winding, but again, it's 3 wires in parallel with each other. 3 or 4 wires. Anyway, let's unwind this and see where the burn is. There's 2 separate windings. They're separated. But you get around 4,000 volts off of a transformer like this, somewhere in that neighborhood. Oh, so actually it is just one big long coil. It's not a center tap. It crosses over from one winding here to the other side of the spool right there, and it just continues on. That looks like that's burnt right there. There's some burning right there. I think this is what happened. Is I think we're going to find a hole around over here. I mean, that crack has actually gone through here. You can actually see it here too. You see where it arced through? I'll just open this up a bit more. It's crispy. And I think this thing didn't even blow the fuse. It just went into automatic shutdown for overcurrent. We'll unwind this side as well. I want to see where all those wires are burned and melted together. It's got awful hot when it failed, that's for sure. Oh yeah. Yeah, let's just break this side off here. We can see with the carnage right there. There's the carnage. Excellent. Okay, now you guys can see what happened. So the core cracked, broke into a couple of little pieces. One of those pieces basically became an arc welder, and wherever it went, one of those pieces became a little arc welder. I had it before. Look at all the shrapnel. This core broke into it's just crumbling. The core is crumbling. It's got so hot. But basically, what happened is the core cracked. It became a little arc welder, and it burned a hole in the insulation here, or in the plastic for the core, the insulation. Burned a hole into that, and then got into the winding and started melting wires. And once the insulation on the wires failed, well, then it was game over. It just the whole core just basically melted in on itself, as you can see. If I take out some more of this now non-existing insulation material, you can see the core itself just basically melted itself together. Oh yeah, look at that, all the insulation shot on there. That was a good meltdown, that one. Okay, I think we're pretty much done on this. This is like a solid block of copper. I can't even separate these windings. Yeah. I guess welded together. Did a good job. Well, at least I think the magnetron's okay, because it tried to come on until it shut down because it was drawing too much current due to the short on the secondary winding. So I think I got some salvageable parts out of this thing. The rest of this is going to go to recycling. I'll just dump this in the bin. Throw all this in the scrap wire bin at work. And before I finish this up, I'm going to salvage a couple parts. I can't resist keeping the output transistor, and there's a big resistor here, a big cement resistor. Those things are expensive. It's like what is it, 3 ohms, 7 watt, 3 ohm. I gotta keep that. I'll keep the transistor. I don't know that I'll need this transistor for anything. Oh, might help if I kept my soldering iron turned on, but I'll keep those. I'll keep the rectifier. Keep the bridge, I'll keep that, and the transistors. Maybe these caps. These are always nice to have. 500 volt rated caps, so I'll keep these caps. I'll keep these caps as well, and the two semis and the resistor, and the rest of the board can go because there's nothing else of any value on here. We'll recycle what we can, right? Or keep what I can just in case I ever need to use it on something else. And taking parts out has become so easy with this new solder tool. Why I dealt with that Weller one for so long that didn't work, I don't know. It'd be nice to have an electric pump, but at what they cost, they are just too much money, and the tips are expensive. Alright, so I've got the heat sink, the transistor, and the rectifier off of here. The rest of this board is, I guess I'll pull these caps as well. I'll just keep these two caps. It's usually easier just to add some leaded solder to the mix. It just makes it melt a little easier. Because this lead-free stuff needs a lot of heat. Oops. Just makes it that much easier just to remove them that way. And I guess that's about it for this one. I'll say thanks for watching, and we'll catch you on the next one real soon. Got to go through some of my stuff here to see what needs to be fixed. So I'll catch you in the next one. Bye.